so we've looked at several examples of things that are continuous, right? Basically, compositions of continuous mappings are continuous. If these mappings have real values, it can add them up, it can take products or ratios, and as long as these are well-defined and everything's continuous. Okay, so far so good, right? So now we're going to backtrack a little bit, and we're going to look at kind of different ways of building continuous function or proving that things are continuous. So before I actually get started, I just want to point something out to you. It's kind of trivial, but it's going to be important for what follows, right? Okay, so this definition of continuity is qualitative, right? So it means that convergence gets mapped to convergence, basically. It doesn't say anything about how fast the convergence takes place on either side, right? Because it's qualitative, you can actually check that if you look at that concept of equivalent metric, right? So what's a metric equivalent to d sub x? It's a metric that if you replace d sub x with this new metric, the concept of convergence doesn't change, right? So one consequence of this qualitative nature of continuity is that if you replace this metric by an equivalent metric on x, if you replace this other metric by an equivalent metric on y, continuity doesn't change. Meaning, if x was continuous before, it continues to be continuous now, and vice versa, right? So there's no change to the concept. Now, there are times in which it's convenient, or it's actually very desirable, to have more quantitative estimates. And these are stronger than what you need for continuity, but in many cases they come for free, right? And perhaps the most basic example is when you have a Lipschitz function. So again, let me take a function f defined over a subset of x to y, given, right, so this is a definition, given a number L greater than 0, well, actually greater or equal to 0, we say that f is L Lipschitz if for any 2 points in D, the domain of f, if you look at how far they are after you apply f, that's never larger than L times their distance before you apply f. Right? So that's basically saying, okay, say L is greater than 1. This means that maybe f of x, well, let's say L is equal to 2, just to make it concrete, right? Maybe the distance between f of x and f of x prime is bigger than the distance between x and x prime, but it's never more than 2 times bigger, or L times bigger, the original distance. Okay. So there is a limit to how far this function can kind of map to points that are close by, and that's related to continuity. Well, in fact, let me notice that such an f has to be continuous at all points. And how do we prove that? Well, it's simple, right? So if I have a sequence f sub n converging to x, everything happening in the domain, right, of the function g. X sub n converges to x. Now I look, what do I hope for? I hope that f of x sub n converges to f of x. Well, in this case, I have a quantitative measure of this convergence in terms of this convergence, because, well, okay, the distance is always non-negative, right? And on the other hand, I know that this is L times dx x sub n x. And then again, in this class, I'm in this sandwich situation, right? So this thing is a sequence of real numbers that's sandwiched between 0 and something that goes to 0, right? That's what this means. Therefore, this goes to 0 as well. So if x sub n goes to x, the distance between x sub n and x goes to 0, and therefore this has to go to 0 as well. So any Lipschitz function is continuous. So when we say Lipschitz, we mean that the function is L Lipschitz for some unspecified L, right? So we're going to be looking at several different Lipschitz functions which can be defined over any metric space. And these are going to come up in many ways later on in the class. Okay, so hopefully the concept is clear by now. So let me define okay, so right. I'm going to fix a point x naught. So now I'm going to be looking at functions from some x, so metric space x dx, and to R with the usual metric. So I'm going to fix a point in the subset of x, and the subset I'm going to assume is non-empty. Otherwise, things are not much fun. And I'm going to define, first of all, this function f naught. And what it does is simply, given a point x, it computes me the distance between x and x naught, which is sort of my reference point. And I claim this function is one Lipschitz, meaning it's Lipschitz with a constant that's 1, right? Okay, how do we prove that? Well, that's basically the triangle inequality, which is more or less the reason why I'm discussing this here. Okay, I want to look at the distance between f0 of x and f0 of x prime, and I want to prove that it's bounded by L equals 1 in this case, right? So I want to prove that this distance is bounded by the distance from x to x prime. Okay, well, f naught of x and f naught of x prime, these guys are real numbers, right? The range of the function, the counter domain of the function is the real line. So the way I measure distances here is by looking at the absolute value of the difference. And these things I can write down in terms of distances, right? So now, okay, I want to use the triangle inequality somehow to upper bound this. So let me look at things that perhaps we can understand come from the triangle inequality. So this distance, to go from x to x naught, I can go from x to x prime, then from x prime to x naught, right? And that gives me an upper bound. That's a triangle inequality. And what does that give me? Well, if I move this guy over here, I have that d sub x, x naught, minus d sub x, x prime, x naught. This is less than d sub x, x prime. That's not exactly what I want because I have an absolute value here, which I have to get here somehow. But now notice that the role of x, right? So everything I'm writing here should be for all x and x prime and x. So now notice that the role of x and x prime here is completely symmetrical, right? So I could could replace this guy by x prime, replace x prime with x, and everything would still work. It's still the triangle inequality. There's a slight change here. Okay, I have to flip these two guys, right? This is x prime now, and this is x. But we know that the distance is symmetric, right? So if I switch these guys, it doesn't really change. So I have another inequality. And now if I combine these two, what I'm showing is that the absolute value of this distance, right, which is one of these two guys, is less than the distance from x to x prime. So I can come back here above, and I have this. And that's what's over here. And therefore, I've shown that the distance between f naught of x and f naught of x prime is at most a distance from x to x prime, which really means that f naught is one Lipschitz as it claimed it was. Okay, good, right? Now here's a slightly more challenging example. So here my function measures the distance from a point to another point, a fixed reference point. A more challenging example is example 2 here. Let me call it f sub x. It takes a little point x, and I'm looking at what people sometimes call the distance from x to the set S, this set S here. And that by definition is the infimum of distances from the point x to elements of the set S. So if you want to think about it geometrically, I have, right, so I have a point x, I have a set S, and this is like computing what this smallest distance to S is, right? We're doing an abstract setting, so with this picture, we shouldn't believe it too much. We should accept it with a grain of salt, but that's intuitively what's being done. You're measuring the shortest distance you can travel from X to reach the set S, more or less. Is also one Lipschitz. And that's a little bit more complicated than the previous case because, because it involves an infimum, right? So, well, okay, first we should check that this function is actually well-defined, right? So for each element little s of the set S, this is a non-negative value. So the set of values like this is a set of real numbers that's bounded from below by 0, right? So all distances are non-negative. So the smallest value that a distance can take is 0. Well, the largest value could be infinite. Maybe there's no largest value. But we know that the set of values is bounded from below. And the set of real numbers that's bounded from below has an infimum, which is a real number. So everything here makes sense. There's no question that this is correct. So now how do you prove this function is Lipschitz, right? So what we want to prove is that, right, so that's what we want. Is it true that fs of x is minus fs of x prime? Is it true that this is less than the distance from x to x prime? Remember I said it was one Lipschitz. Well, okay, it might not be so clear, right? Okay, we need this with the absolute value, right? The distance between f sub s of x and f sub x to x prime should not be greater than the distance from x to x prime. And this is not s, this is x. Okay, so how do we prove this? First of all, let me notice that as before, we can drop the absolute value, right? So if I prove that this is true, then I have the same inequality with x and x prime reversed. And when I reverse here, I don't really change anything. So again, if I have an inequality in this direction, I have an inequality for the absolute value. And let me notice that this thing that I want to prove, I can rephrase it as this. Right? So this is what I want here. Let me write it like this. So this is what I want to show for any x and x prime. Okay, there are different ways of doing this. Let's rewrite what this means by definition, right? So this thing here is the infimum of little s belonging to s of dx x s. And let me write it like this, just to have fun. And this is the infimum over s belonging to s of, I'm going to, x prime s. I'm going to do something that maybe you're not expecting here. And then I'm going to try to explain what I mean. I claim that this thing at the top is the same thing as at the bottom, right? So that if checking one thing is equivalent to checking the other. Well, okay, how is that? Okay, this is clearly equal to this, right? F sub s of x prime is the infimum of this part without this other guy. So how come I can put this guy inside the infimum? Notice that this thing here does not involve s. I'm taking an infimum over s, and this term does not have s, right? So I'm looking at the set of these values, and I want to take its infimum, and then I want to adopt this quantity. But it's the same as summing this quantity before. Okay, what I'm saying is that if I have a set of values, and I add the same number to all of these values, this number does not depend on s, the infimum gets shifted by this amount. So basically I'm saying, okay, if we put the brackets of the infimum here or here, this doesn't really change anything. And if you don't believe that, well, you should go back to your analysis over the real line. It's an exercise. It basically means, okay, taking the infimum is like minimizing, so I want to minimize the sum, but this term doesn't really involve s, so I just have to take care of this guy. And this gives me this. Okay, and why is this true? Now it's obvious, because by the triangle inequality, I have an inequality in the right direction. So the distance from x to s is less than the distance from x to x prime, plus the distance to x prime to s, from x prime to s, sorry. So I'm saying all of these numbers are upper bounded by these, and then you know that, okay, you're minimizing this, and you're minimizing this thing which is bigger than this. So of course the minimum here, the infimum, if you want to be more formal, is bigger here than here, because these guys are always smaller than these guys. So again, I'm using factorial analysis over R, but I hope that's not too complicated. So basically the idea is that I could look at it this way. Look, I'm going to take, first of all, hide this infimum here, hide this infimum there. I know that this is less than this sum by the triangle inequality. This holds for any s, in particular if I take an infimum here, that's true for any s. And then I can take an infimum there as well, and I get this. Okay, so this function that computes a distance to a set is something that we keep coming back to over time. Right, and any other examples? Not that I want to discuss right now. We're going to be talking about many other examples, especially coming from specific spaces, but not like this sort of general thing of over general metric spaces, right? I do want to finish though by mentioning a couple of things that we're going to get to in the next video. Of course, we have the space that we have been studying, this vector space of continuous functions with the soup form. So this, we can think, this is a vector space with a norm. We know it's complete by now. We can also think of it as a metric space because we know that the norm gives us a metric, a way to measure distances between functions, elements of C. And we can consider functions, say, from mappings from C to R, say, or from C to C, right? It's sort of maybe a little bit difficult to wrap your head around these because I'm looking at a function whose input or whose domain is the set of functions. And then I'm saying, okay, I have something that takes a function as an input and produces a real number as an output. So that looks kind of funny, right? So, well, historically, that's the reason why people call functions over functions functionals, like we describe linear functionals, right? So, okay, let me give you a very simple linear functional, which we'll show is continuous in the next video. It's this integral thing, which takes an f and computes its integral over the interval, 0, 1. So this is well defined. This takes a function and produces a real number. So it's a function from C to R. And we're going to argue that it's a continuous function. It's actually a continuous linear functional because we've seen already this is a linear function. And we're going to give a criterion that says when a linear function, or more generally, linear transformation, is a continuous mapping from one state to another. And then we're going to see some nonlinear examples as well. And that's it for now. Thank you.